Last time we discussed in detail, at least in the Riemannian case, how to show that if h is bigger than or equal than 0, then I give an alternative proof. For this fundamental inequality, here I recall that V of x r is the volume of the geodesic ball centered at x with radius r. So I want to now expand a little bit the horizon here and move from, as I started to do last time, from the Riemannian case to the sub-Riemannian, or at least some large classes of sub-Riemannian manifolds. So let me just quickly recall the setup from last time. We have a C-infinity manifold without Riemannian structure on it at the beginning, and we have a diffusion. So a diffusion operator with real coefficients. So real coefficients. We made various assumptions. L1 is 0, so there are no zero-order terms. And then L is formally, so there is also M is endowed with a smooth measure. So this is a measure from M. It does not, in fact, in general, it will not be the Riemannian measure, but we just assume that there is a smooth measure, and L is formally self-adjoint with respect to mu. Okay, so we consider
excuse me, Nicola. Can you recall in which sense do you understand diffusion operator?
This is just an operator which has a semi-definite quadratic form associated to it. So in local coordinates, you can write it like this. And the quadratic form is semi-definite positive. Does not have to be positive. So for instance, this includes also the heat equation. Okay? So, and many more operators. But the assumptions I'm making is that L is formally self-adjoint with respect to mu. And also, remember, important assumption is that L is locally epsilon sub-elliptic. So it satisfies a subelliptic estimate with Sobolev space in the left-hand side with exponent epsilon. Epsilon is a fractional number in general, and it depends on the operator F. Okay? So, but I'm not assuming, of course, that L be elliptic, because then we will be back in the Riemannian case. All right, so under these assumptions, I defined a Carré-Duchamp. So Carré-Duchamp, which is canonically associated with L, is 1/2 L of F squared minus 2 F L F. F here is any smooth function from M. So there is a Carré-Duchamp, and there is also a canonically associated distance with L, which is, it takes some time to define it, and I do not want to dedicate my last lecture to defining all these things. So I will just say that there is a distance, a canonical distance, which is very well known to people in this audience, and this is normally called the Carnot-Caratedori distance, or control distance. Let's call it control distance. Many people after Gromov call it CC Carnot-Caratedori distance. So there is a notion of a subunit vector associated with this operator at one point, and then you take all those curves which are for which the tangent vector is subunit with respect to L, and then you minimize on the length of these curves, and that gives you this control distance. This control distance, of course, in the Riemannian case is just a standard Riemannian distance, but otherwise it can be a very, very wide distance, and it's not easy to put your hands on it. But there is a fundamental theorem of Chow and Rashevsky that goes back to 1938. Rashevsky and 1939 Chow, that says that if L is of this form here, so if L is a sum of square of vector fields, and these vector fields are infinity of M, in these cases, to be connected. This is important. So M is connected, and the vector fields are smooth and satisfy the so-called finite rank condition. Finite rank condition. So this means that at every point the vector fields and a sufficiently large number of their commutators span the tangent space. Then dxy is a true distance. Is a true distance. Of course, this distance, this so-called control distance, you can define it, and you don't know a priori one basic property. I mean, it's easy to check all the properties of distance, except that the dxy is finite for every couple of x and y. So dxy finite is equivalent to saying that for any 2 points, there is at least one of these subunit curves that joins x to y. And this theorem of Rashevsky and Chow guarantees that under this assumption, the control distance is in fact finite. So there is, for every 2 points, there is a possibility of connecting them with one of these subunit curves. Okay. So that is the control distance. There is also another distance which is very convenient to use and which is also canonically associated with this operator, and that is the distance that you can define like this. So the fxy equals the supremum of fx minus fy, where f, let's say, is 0 infinity on M, and gamma of f, gamma is this object here, is the Carré-Duchamp, is less than or equal to 1. And you can show that many people say that these two things are the same. This is not true in general, unless you make a basic assumption that any 2 points can be connected. If you assume the connectivity, then you can actually prove, and it's a theorem, that the dxy is equal to dl xy. So these two distances are the same. Okay. So I will denote routinely with the bxr the balls in this distance, either one of these two distances, because I will assume throughout the connectivity assumption. Okay. So, all right, so given a diffusion operator L, we have a Carré-Duchamp attached to L, and then, of course, like in the Riemannian case, we can define the higher order bilinear form in this way. So we have 1/2 L of gamma of F minus gamma minus twice gamma of F LF. Okay, so so now I have operator L, Carré-Duchamp, I have this gamma 2. Okay, so it seems like I can start the same game that I did in the Riemannian case, and maybe that I will get somewhere. Unfortunately, that is not the case. The reason is that in sub-Riemannian geometry, the Carré-Duchamp and this quantity here, they only capture differentiation in horizontal directions. However, there is a third direction which is missing. For instance, in the example that I have given of the Heisenberg group, you know, remember the example that we discussed last time of the Heisenberg group. So the non-commutative group law. Then we have L, which is given by x squared plus y squared, where x was dx minus y over 2 dz, and y dy plus x over 2 dz. But then there is also the missing direction, which is important here. And in order to define a notion of curvature, which is useful, you will see that we need to take into account the missing direction. Now, in the Heisenberg group model, which I would like you to keep in mind, because it's a very simple quote-unquote model, which already has some of the subtleties of the situation. We know that there is this other vector field here, which comes from taking the differential or left translation of the third direction, dvz. So this vector field here is connected to x and y by this commutation relation. Okay, so in order to develop a notion of curvature in sub-Riemannian geometry, we need to take into account this object here. So I will also assume then, I will go back to this general situation, but keep this example in mind because it's good to keep it in mind. I will also assume that besides the operator L, there is also another bilinear form on the manifold. So I will impose it from outside. So I will impose that there is another bilinear form on the manifold, and I will denote it gamma z, which satisfies Leibniz rules. So gamma z of fg h is equal to f gamma z gh plus g gamma z fh, and which satisfies gamma z of f. This, by definition, as before, will be gamma z f. This is generally than 0. So I will make these two assumptions. There exists a bilinear form gamma z on smooth functions, which has these two properties here. And this is not over yet. I have to make more assumptions. So now, connected to this gamma z, there is also going to be a gamma 2 z f, which, as you can imagine, is going to be L of gamma z f minus 2 gamma z f L f. So there is a higher order bilinear form associated with this gamma z. Let's go back to the model. Here, gamma z in the model, let me tell you what gamma z is. So gamma z of f and g is simply zf zg, where z is differentiation in the vertical direction. Okay, so this is the model that you have to keep in mind. More in general, you know, there will be many vector fields like this, at least locally, and then you have to put some structure on the tangent space, but that's okay. Okay? So I will assume that there is this gamma z. So now I have L, gamma, and gamma z. So I have three objects here. And at this point I will introduce the basic, oh, by the way, in the Riemannian case, gamma z is identical equal to 0. Let's keep this in mind, okay? Gamma z does not exist in the Riemannian case. It only exists in the truly sub-Riemannian case. So you have to think of gamma z as the differentiation, the Le Carré-Duchamp along the vertical directions. So and now I will introduce the main character, the generalized curvature dimension inequality. So I will say that the manifold M satisfies the generalized curvature dimension inequality with respect to L and gamma Z if there exist numbers rho 1, rho 2, kappa, and D. So M satisfies, so this is definition. This definition is due to Padova and myself. Satisfies curvature dimension inequality with respect to parameter rho 1, rho 2, kappa, and D with respect to M, to L, and gamma Z if the following happens. So if for any f in the infinity of M and for any nu bigger than 0, gamma 2 of f plus nu times gamma 2 z of f is bigger than or equal than 1 over d times LF squared plus rho 1 minus kappa over nu times gamma f plus rho 2 gamma z f. Okay, so that's definition of curvature dimension inequality. Well, looks like a strange definition. Where does it come from? I will not tell you right now where it comes from, okay? I will wait a little bit because I want to say a few more things before I tell you where it comes from. So, this inequality has to hold for any function f and for any positive parameter nu. Notice a few things. Riemannian case, so I'm going to erase here, you have to remember these things. Let's compare with the curvature dimension inequality CD rho 1 n in the Riemannian case. Riemannian case was this bigger than or equal than 1 over n times Laplacian f squared plus rho 1 gamma f. Now, if we are in the Riemannian case, then L is just going to be the Laplace-Beltrami operator. I'm going to take L as the Laplace-Beltrami operator. And therefore, gamma z is identical equal to 0 because there are no vertical directions. I mean, the tangent space is completed by the local representation of the vector fields of the Laplacian. So, and I can take, in this inequality, I can take kappa equal to 0, and then you see that this inequality becomes this one, with d equal the dimension of the manifold. This is not here. This is 1 over m times Laplacian f squared. Kappa is 0, rho 1. And then I take gamma z identical equal to 0, so this is gone. And so the curvature dimension inequality, the generalized curvature dimension inequality, is nothing more than just the standard curvature dimension inequality of Bakry-Emery. So this is a new object, but it's not so new in a way, because first of all, it encompasses the Riemannian case, which is good. However, this is actually a completely new object. So let me show you that it covers situations which are genuinely non-Riemannian. And one of them is the following. So let me discuss the three-dimensional Sasakian model. So let me consider rho 1 is a real number, and I construct a Lie group in the following way. I look at the Lie group, which I will indicate with G of rho 1, of the group whose Lie algebra is the span of x, y, z, three elements. So this is going to be a three-dimensional group. And I impose on this elements the following commutation relation. So x commutator with bracket y is equal to z, 1, 2, x bracket z is equal to minus rho 1 y, and 3, x bracket y bracket z is equal to rho 1 x. Okay? So I can always construct a Lie group like this. I mean, the Baker-Campbell-Hausdorff formula and the bracket relation will tell me immediately what is the group law. And so this becomes a Lie group. And then notice that the fact that the bracket between x and y is equal to z guarantees, because of Ormander's hypolyticity 1967 theorem, which I quoted last time, guarantees that this operator L equal to x squared plus y squared is hyperelliptic. And in fact, it is locally epsilon equal 1/2 sub-elliptic. Okay? So this model here, this operator is hyperelliptic, but L is not elliptic at any point of G of rho 1. So L fails to be elliptic at every point. Fine. And then you can do some calculations based on the fact that you can observe that from this commutation relations, from the definition of L, you can show that the commutator bracket from L and between L and Z is 0. So if you use this fact and you do your calculations, you can show, it's an exercise, you can show that this Lie group here satisfies. So here I have L, then I have gamma, and now I have gamma z. Gamma z is what you think should be. It's the same as for the Heisenberg group. Gamma zf is zf squared. So it's a Carré-Duchamp along the z direction. And then you can prove that L with respect to G with respect to L and gamma z satisfies a generalized curvature-dimension inequality of this kind. So satisfies, I don't remember exactly the values of the parameters, but they are here. So satisfies the generalized curvature-dimension inequality CD rho 1. Rho 1 is the parameter that appears in these assumptions here. CD rho 1, 1/2, 1, and 2. So let's compare with this. So rho 1 is going to be the parameter. The rho 2 in this inequality here, the number that appears in front of this guy here is going to be 1/2. Kappa, the number that appears here, is going to be 1. And this d, this strange dimension, so to speak, is going to be 2. Okay, so the dimension is going to be 1 dimension less with respect to the dimension of the group. So this is an example of an object which is purely sub-Riemannian. It satisfies an inequality like this, but it will never satisfy an inequality like this. Okay? And in order to prove that inequality, you need to have this vertical direction. So you need to have this gamma z, and you need to have the corresponding gamma 2z coming from the gamma z. All right, so what is going on with this? Why is this thing interesting? Because you can show, again, it takes some work. You can show that there is a complex structure associated with this group. So for any Lie group constructed in this way, so G rho 1 has a canonically associated complex structure. I will not go into the details, otherwise I'll take all this.
Excuse me, this group is three-dimensional.
Yes.
What is the complex structure in the case of odd dimension?
Oh, well, CR structures, they are all dimensional. So, yeah.
If ρ1 is equal to 1, this is the algebra SU2.
I'm about to talk about this. Thank you. So, let's go back to your question. CR manifolds, they are all odd dimensional because CR model okay, so you have 2n plus 1. Okay? So CR manifold, they all have odd dimension. And these are, I was about to say, this is so canonically associated complex structure, which makes it a Cauchy-Riemann manifold, a CR manifold. A three-dimensional Cauchy-Riemann manifold. In this Cauchy-Riemann manifold, there is the Reed vector field. The Reed vector field, if you do your calculations, is precisely minus z. So what does it mean? It means that in this example, not only L is gamma is canonically associated with L once that you decide your vector fields, but also gamma z is canonically associated with L because it comes from the Reed vector field, and the Reed vector field in every CR manifold is canonically associated with the sub-Laplacian. So this is the sub-Laplacian, and the Reed vector field is decided by the complex structure once you decide what the sub-Laplacian is. Okay. So you can also check another important thing in these examples, that gamma of f, gamma z of f, is equal to gamma z f gamma f. So in other words, there is some kind of commutation between the Carré-Duchamps. This analytical condition that you can check corresponds to a very important geometric property. These CR manifolds are Sasakian manifolds. In other words, the Tanaka-Webster torsion, so this is equivalent to proving that the Tanaka-Webster torsion or CR torsion is identically equal to 0. So there is no torsion in this manifold. Okay, now let me go to your observation. So let me discuss just very short. In this CR structure, you can also compute and look at Tanaka-Webster. So at the models, what are the models of constant Tanaka-Webster sectional curvature? The 3D models, so 3D models of constant Tanaka-Webster sectional curvature are precisely these groups. And their sectional curvature is equal to rho 1. So this parameter, rho 1, appearing in this purely analytical assumption as the meaning of a curvature when you look at the geometry behind these groups. So these are the models of Tanaka-Webster constant sectional curvature rho 1. Well, and we know what these models are. When rho 1 is equal to 1, so when rho 1 is equal to 1, we get a compact model. So rho 1 equals 1, we get SU2. Okay? And when rho 1 is equal to 0, look at this model. Rho 1 equals 0, it means that X, only this commutator is non-trivial, and it's Z, and these commutators are trivial. We are back into the Heisenberg group. So the Heisenberg group is the correspondent of flat space in Euclidean geometry. Is the model space of constant zero sectional curvature. Okay? And rho 1 equals to minus 1, we get SL2. And so this is the analog of the unit sphere. This is the analog of Rn. This is the analog of hyperbolic space in CR geometry.
But SL2 is not isometric group.
No.
We need to Z2.
And also you should notice that, you know, while this one is nilpotent, this one is not nilpotent. So you don't need to have a nilpotent Lie group. And it's also important. Okay, so so this is the general situation. That's this model here. So now I will discuss a little bit. From now on, you have to keep in mind that there is going to be another assumption added to the picture, and it's this one. So this one is going to be part of the assumption. And then in the end I will discuss a little bit this thing. So I will assume that there is manifold M, operator L, a priori imposed from the outside by linear form gamma z, for which manifold M, L and gamma z satisfies this condition here. And I will also assume that the gamma, which is canonically associated with L, and gamma z satisfy this condition here. This condition is important for making the calculations manageable, essentially. In concrete terms, this condition means that in the models we are in the Sasakian case. So we cannot incorporate all CR manifolds, but we have to restrict to CR manifolds which have zero torsion. We still do not know how to go beyond the zero torsion model. So this is a very interesting open question because this curvature-dimension inequality becomes more complicated if torsion is not zero. Now this is an assumption, but this assumption it's time to tell you where it comes from. So I will very briefly tell you where this comes from. We did not pull this from hat. If you remember the Riemannian case, this condition here is equivalent to Ricci bigger than or equal than rho 1. So the way we arrived at this thing, it took us a long time for us to arrive at this thing because we started from a Bochner identity. So we started working out some kind of sub-Riemannian Bochner identity. And this Bochner identity became a monster. It had lots of terms because of non-commutation. You know, it became a monster, it became unmanageable. And then at some point, we realized that from this Bochner identity, if we impose this condition here, which at the beginning we did not know that it was in fact a geometric condition. For us, it was purely analytical at that time. If we impose this condition, then we could come up with this inequality here, which was giving us results. And then we did all the work a posteriori and discovered that this is in fact a geometric assumption on the manifold. Okay, so that's, I told you a little bit the short story of this thing. Now, when you have a condition like this, you need more. The problem with this sub-Riemannian setting, by the way, all I'm saying has to do with sub-Riemannian manifolds of rank 2. Why rank 2? Because this gamma z is only in the vertical direction. But if I have a manifold of rank 3, for instance, then like the Engels group, for instance, which is a Lie group of rank 3, or like the Mumford, the Lie group associated with the Mumford operator, then you need a further Carré-Duchamp in the higher direction. And then more Carré-Duchamps you need, more Bochner identities you need to prove. And the most difficult one is the one in the horizontal layer. But in other words, you have to look at L of gamma f. Remember, Laplacian of gradient f squared. But then you have to look also at L of gamma zf if you have rank 2. So you need two Bochner's identity, and you need to play them one against the other. If you have a group, for instance, a group of strep 3, of rank 3, or a manifold of rank 3, then you need to look at the third. So you have another direction, L, let's call it gamma W. Yeah. And then you will have three Bochner's identity, and you have to play them one against the other to come up with a curvature-dimension inequality, which will be much more complicated than this, because here you will have also gamma W2. You see what I'm saying? I mean, the higher is the rank of the manifold, the more complicated this thing becomes. So this situation describes only one particular class of manifolds, manifolds of rank 2. We do not know at this moment how to go beyond rank 2 yet. So we know what we would like to do, but we don't know how to work it out. I mean, the technical details are heavy. Okay, so, but anyhow, so this is the situation that we know how to deal with at this moment, and it's a genuinely sub-Riemannian situation, as you see. And in this, I mean, this condition includes a very large class of sub-Riemannian manifolds. Very large class of sub-Riemannian manifolds. I mean, I cannot go into description of geometric description of these models, but it's, you know, in my paper with Gold 1. And once we have that curvature-dimension inequality, then we can crank the machine, which I tried to illustrate in the Riemannian case. and then we start proving some results which I think are new, quite new and interesting. And so let me now, I think that I should probably stop soon.
Yeah, 5 minutes.
To stop in 5 minutes, so I can talk. Okay, okay, good. So the first thing that, so the idea here is that once these hypotheses are in place, all the results come exclusively from this inequality here. Exclusively. Okay? So we don't need anything else. And the first thing that we prove is a Liao inequality. So, well, I'm going to just write down the Liao inequality without telling you much about it. So, I assume the curvature-dimension inequality, ρ1, ρ2, kappa. Remember, in this curvature-dimension inequality, only this parameter is truly important.
Geometry.
This parameter is where the geometry is. So this is a Ricci lower bound. For instance, we can show that all kernel groups of step 2 satisfy an inequality like this with ρ1 equal to 0. So kernel groups of step 2 are Ricci flat, Ricci bigger than or equal than 0.
And D is Hausdorff dimension.
D is, for kernel groups, D is just the dimension of the horizontal layer. Okay? And then there are numbers ρ2 and kappa that you can define, and they depend just from universal constants of the group. So, this is the parameter which is important. This says that there is a certain Ricci tensor for which Ricci is bigger, sub-Riemannian Ricci tensor. In the models, in the Sasakian models, you can show that this number ρ1 is precisely the lower bound on the Tanaka-Webster horizontal Ricci tensor. So it's geometrical. Okay? So I will assume this, and then attached to this there is this inequality here. So so I will just write it. Log of PTF. Here, as always, F is C0 infinity on M, and F is bigger than or equal to 0. And then we have here less than or equal than 1 plus 3 kappa over ρ2 minus 2 ρ1 e over 3. And here there is L PTF over PTF plus, just bear with me, I mean I will finish immediately, T over 6. I mean there are all these numbers floating around because the Liao inequality becomes more complicated in the sub-Riemannian case. But as you will see, it gives back the Riemannian plus d over 2t, and then there is here 1 plus 3 kappa over 2 ρ2 squared. Okay? So this is the Liao inequality that we obtain. Now let's look for a second, let's compare this with the Liao inequality in the Riemannian case. Riemannian case, remember, gamma z is identical equal to 0. So this term is not here. Gamma z is 0. Kappa is also 0. So this is not here. This is not here. And this is not here in the Riemannian case. If I take ρ1 0, I get exactly the Riemannian-Liao inequality. Gamma of log of PTF minus dt log of PTF less than or equal than n over 2t if I take d equals to n. It's in here. Just look at this inequality. This is gone. This is gone in the Riemannian case. If I take rho 1 Ricci bigger than or equal than 0, so rho 1 is 0, this is gone, I get just Laplacian of pt over pt. Since the Laplacian of pt is ddt, so this is ddt on log of pt. So I get minus, brings to the left hand side, this, rho 1 is 0, rho 1 is 0, here I get this, n over 2t. That's and it gives a very nice introduction to CR manifolds. I mean, it starts from the beginning and it gets to the theorems.
You say Wien, Dragomir, it seems Slavic name.
It's a Slavic. I think it's Romanian. So
what is Slavic?
So what is the correct pronunciation? Dragomir or?
Yeah.
Okay, Dragomir. Okay. Thank you. All right. So let me then continue. And of course,
Do you hear some similarity between Dragomir and Vladimir? They're very close.
yeah, they're very close. Well, of course, besides thanking Sergei for the invitation, I should also thank the very kind audience for putting up with me. Okay, so let's see. So let's erase the. I already pointed out that this inequality encompasses the Riemannian one with sharp constants. And now what I will do so let me point out that if inequality CD, rho 1, rho 2, kappa and d holds for a certain rho 1, it also holds for a certain rho 1 prime smaller than rho 1, trivially.
Excuse me.
Because I go down, putting a
stupid question.
Sure.
What is PT in this sector?
Is PT is the heat semigroup
PT
associated.
minus L.
PTF is EPL.
Oh.
Yeah. So in this, you can show by functional analysis that there is a positive function which is C infinity. This is non-trivial because this comes from this local sublimity. This is
also a solution of some.
It's solution of the heat of the Cauchy problem. So there is this measure mu, and this satisfies LF equals FP. So the Cauchy problem with Fx, maybe I should call this U. So, sorry, Lu equal Ut with Ux0 equals Fx on the manifold. Okay? You missed crucial lecture on this thing, so no, I know, I'm joking. It's okay. So I was saying before that if this one holds for a certain rho 1, then automatically holds for rho 1 prime less than or equal than rho 1, because you see, you go down this way. Therefore, I will assume from now on some kind of the analog of so just think of it as Ricci bigger than or equal than 0. I will assume this this inequality, just for simplicity, okay? To keep things to simplest possible level. So if ρ1 is 0, then here I can get rid of this. ρ1 is 0, so I don't have this. I don't have this. I don't have this. And that's it. So the inequality simplifies, becomes this one. Also notice that this one is a bonus, is our friend, because I'm going in this direction with the inequality. T is bigger than 0, this is bigger than or equal than 0 because it's a Carré-Duchamp. So I could go down removing this. Is it clear? If this inequality holds, then also the one without this holds trivially, because this term is bigger than or equal than 0, and I can go down. Okay? So, first thing first property that follows from this inequality is, so from this Liao inequality, we get the following theorem. So this is mod 1 and myself, and it's going to appear in the Journal of European Math Society at some time. I mean, it took them a long time to refer these papers, something like 5 years. Paper was submitted 5 years ago. Finally, after 5 years, it's going to appear. So, 5 years and many, many reviewers. I think I know what the problem is. Paper was sent to geometers. Geometers don't like analysts getting into their turf. So geometers refused to refer the paper. So paper was sent to analysts. Analysts did not understand the geometry. So analysts refused to refer the paper. Paper was sent to a geometer again. And it was a kind of circle. So,
what is the name of journal?
GEMS, Journal of European Math Society. Yeah. Okay. So theorem. So this is Harnack inequality. Harnack inequality. So suppose C, D, 0, ρ2, kappa, and D for some ρ2 positive, kappa bigger than or equal than 0, and D positive. Okay? Then there exists a constant which depends on ρ2, kappa, and D bigger than 0, such that for any f in C0, no, let's forget that. Let's just work with the heat kernel, which is an important thing. Okay? So let's just work with the heat kernel such that for any x and m, x and y in m, and for any 0 less than s less than t less than infinity, we have x, y, and z, sorry. So p, x, y, s less than or equal than p, x, z, t. And then I have t over s to the q over 2. I will tell you in a moment what this number q is. And then I have x of q over d, d, x, y, d, y, z, d, y, z squared over 4 p minus s. And q is the number d times 1 plus 3 kappa over 2 ρ2. Okay, it's what it is. Yeah. So this is what we get. So this is a scale invariant uniform Harnack inequality for the heat kernel. So we get that the heat kernel satisfies this inequality here. Notice that there is a gap between S and T, like in the Riemannian case. So if reach is bigger than or equal than 0, then we have this inequality here. Okay? Now, once that we have this inequality here, then we can get this result. So I'm just going to give you now a survey of what we proved, without going into any technical details, because I have covered already. This inequality here comes from the Liao inequality that I proved before. Okay? So it's essentially it's the same proof that I gave you in the Riemannian case, except that the numbers change. Notice that in the Riemannian case, kappa is 0, and so this Q is just the dimension of the Riemannian manifold, so this number is 1. And this is n over 2. Okay? So this contains the Riemannian case, but since we are in the genuinely non-Riemannian situation, we get these numbers here which are not best possible. These numbers are not best possible. I want to emphasize it. How do I know that they are not best possible? If I check the situation on a kernel group where I have scalings, then I see that in kernel groups I should get here 1, and I should get here the homogeneous dimension of the group, because I know dilations, I have dilations, so I can just prove these estimates by dilations. Okay, so a consequence of this theorem is this other theorem, which is off-diagonal Gaussian upper bounds. So, and what we prove, again, the assumption is always going to be this one. So I will not list every time. So what we show is this. There is a constant here, which depends on ρ2, kappa, d, and epsilon. You will see that there is an epsilon in this estimate here. And here I have the volume of the ball centered at x with radius square root t to the 1/2. The volume of the ball centered at y with radius square root t to the 1/2. And then here we have x of minus b x and y squared over 4 1 plus epsilon t. So the statement is, for any epsilon, there exists a constant which depends on this parameter and on epsilon, for which this estimate is true. If epsilon goes to 0, this number blows up. So you cannot improve this. You cannot let epsilon go to 0 here, because number is going to blow up. Now, yeah, this theorem follows from this theorem here, and from a fairly involved proof. But anyhow, it's so we get this off-diagonal Gaussian upper bound. Notice the appearance of this object here. This is the enemy, because you don't know how to relate one to the other. So we have to wait a little bit for that. Okay, so, and now I come to the, so let me call this theorem number 1, which follows from Liao, and then we get theorem number 2, which follows from Liao, and theorem number 1.
Excuse me, it's a little strange. You have here on the exponent positive number.
Yeah, no, this is not strange because this is the heat kernel. Okay?
And there is negative, yeah? Okay.
Yeah, that is negative, that is correct. Because think of the heat kernel in Euclidean, flat Euclidean space. Okay? You have a negative there. But this is Harnack inequality is different. I am already taking into account is I have a quotient of two heat kernels. So quotient of two heat kernels produces a plus there. Okay? Alright, so then theorem number 3. In this theorem number 3, there is Padova. There is also Michel Bonnefond. In the case rho 1 equal to 0, and there is my student Isidro Munive. In the case rho 1 any real number. So it's a theorem with it appeared in 2 different papers. So this theorem says the following: there exists a number A between 0 and 1. A depending on rho 1. Sorry, rho 1 is 0. So let me assume rho 1 0. Okay. So rho 2, kappa, and d such that for any x in M and for any r bigger than 0, the heat semigroup evaluated at a r squared of the indicator function of the Carnot-Caratellori ball centered at x with radius r, evaluated at x is bigger than or equal to the universal constant, 1/2. Okay? Now, as I showed you last time in the Riemannian case, once you have an estimate like this, then it's you combine it with the Harnack inequality, which is written here, in a standard fashion, and you obtain the following theorem. Always the same people involved. There exists a constant C, which depends on rho 2, kappa, and d, bigger than 0, such that the volume of the ball centered at x with radius 2r is controlled by C times the volume of the ball centered at x with radius r for any x in M and for any r bigger than 0. So we get the uniform doubling condition for the Carnot-Caratellori balls. So this is the first time that the doubling condition is not just assumed, but it's not an assumption, it's proved. And I have illustrated how, in the Riemannian case, we can get this inequality purely from, it's very surprising because we get it purely from a differential identity between functions, the Bochner identity. In the sub-Riemannian case, the situation is a little bit more involved. We have to work considerably harder to get this, but the idea is essentially the same, except that, so this follows from purely from this Bochner's identity, which are hidden inside the generalized curvature-dimension inequality. Well, this is in the case in which rho 1 is 0, of course. There is a more complicated statement when rho 1 is arbitrary real number. But I'm just telling you what is the case, rho 1 equal to 0. All right, so at this point, the situation starts becoming quite exciting, because once you have this doubling condition here, and you have this Harnack inequality here, then you can implement a very powerful circle of ideas that goes back to a paper 1986 by Fabes and Struck, and that subsequently was developed by Alex Grigorian in 1991 and independently by Laurent Saloff-Coste in 1992. And and then further was developed by Carl Theodor Sturm in a sequel of papers 1994 to 1996. So if you, and there is, and I should not forget, a fundamental paper by Kusuoka and Struck, which is 1987. So when you put together all these ideas, then you can show that you can get the off-diagonal Gaussian lower bound. So in other words, you can reverse this. You can put a bigger than or equal here, and you can remove one of these two. So you can put here, remove, all right. So why don't I write it? So dx y t is less than or equal than constant. I'll write just c epsilon. The other parameters are implicit, and here I get dx square root t x or minus dxy squared over 4 1 plus epsilon t, and here I get c epsilon to the minus 1 x, I'm sorry, divided by v x square root t, and then x of minus dxy squared over 4 1 minus epsilon. Notice the minus, okay? So one gets this estimate here. So one gets a global estimate from above, Gaussian estimate from above and from below. Notice that this object has disappeared. It has been incorporated here. The possibility of doing that is due to this theorem 4. Okay? So it takes some little, but it's standard work by now. Once you have little theorem 4, and then you know, you have to do some work to get this estimate from below, and the estimate from above, you get improve it like this. So now we have Gaussian estimate from below, from above, we have doubly condition, then Kusuoka and Struck tell us how to prove another very important inequality in analysis, which is the so-called Poincare inequality. So once again, I mean, once you have these results up to here, then everything becomes very important, fundamental, but by now standard machinery. So now theorem 6, we get the Poincare inequality. That says that if you have a function f, which is, say, Lipschitz on a Tanaka-Webster pole, closure of the Tanaka-Webster pole, then the integral over bxr of f minus fr squared with respect to the mu, so fr is the average of f over bfr. So this is controlled by c times r squared times the integral over bxr of gamma f dmu. So this is a fundamental inequality in analysis. Once again, in sub-Riemannian geometry, this is the first time this inequality is not assumed, but is proved. And this is under the assumption that Ricci is bigger than or equal than 0.
In another way, this is, how to call this, gamma of f.
Gamma of f is,
Gamma is some kind of...
this is the horizontal gradient square.
Yeah.
Yeah. In case you have, you know, sum of squares of vector field, it's just the sum of xjf squared. Okay, so after we have all these things, then we can go back and close the circle. Notice that the Harnack inequality that I proved before was only involving The heat kernel is a global object, okay? But now we have Harnack inequality, we have Poincaré inequality, we have doubling conditions, so that this is a standard machinery in analysis. You can develop the Georgi-Nash-Moser theory and prove a localized scaling variant Harnack inequality for the heat equation associated with Hell. And then once you have that, then you can prove lots of results in analysis. But for instance, one thing that we can show is, the finite dimensionality of harmonic functions. So suppose we have Ricci bigger than or equal than 0. There is a famous conjecture by Liao that says that the harmonic function on a complete manifold with Ricci bigger than or equal than 0, which a polynomial growth at infinity must be finite dimensional, which is a generalization of Newton's theorem. When polynomial growth is like a constant, then you get constants, dimension 1. Okay? So this conjecture of Liao was resolved in 1990 in a in the Riemannian case, in a sequence of fundamental papers by Holding and Nicola. So there is a sequence of papers by Holding and Nicola in which they prove Liao's conjecture. So now we can get an extension because of all these results. We can prove Liao's conjecture in the at least in the sub-Riemannian manifold that we deal with. So if we look at harmonic functions, solutions of L of f equals 0, which have a polynomial growth, so f of x is less than or equal to c1 plus distance x to some fixed point to the alpha, then show that the space of this function is finite dimensional. And we can do this. So in particular, we get that under Ricci bigger than or equal than 0, harmonic functions which are bounded are